Okay, I want to lead up to second order equations with constant coefficients. This is a first order equation with a constant coefficient, right? Another way to solve this is to let y equal e to the rt. Okay? Well, if y equals e to the rt, then what's y prime?
RE to the RT?
No. Chain rule.
With respect to R or T?
Yeah, what do we do with respect to what?
That's a good question. Let me write it this way. And I kind of automatically went to t instead of x as a variable, okay? Now y is a function of t, okay? And we'll use t's and x's. And I just kind of naturally went to t here without warning you, okay? Now what's the derivative of e to the rt?
T times e to the RT.
Okay, well, you got the right idea. What's the derivative of RT with respect to t? It's RE to the RT, right? So we get RE to the RT plus 2y plus 2e to the RT equals 0. Can you solve that equation for R? What's the first thing you have to do to solve it for R?
Subtract one of the sides over.
I'm sorry, I can't hear you over the hall.
Subtract one of the sides over.
Say that, yell it at me.
Subtract, you could like subtract 2 times e to the RT over. And then
I wouldn't
divide by
necessarily do that, but that wouldn't hurt.
You could factor out E to the RT.
Yeah, as a matter of fact, e to the RT can't ever be 0, so you can just divide the sucker out, right? You can divide by any non-zero, and you're not going to lose any solutions, okay? So you get R plus 2 equals 0. Can you solve that for R? Well, I'm going to skip a step here. Fill it in if you need to. R equals -2. And I know you don't need to fill that in, okay? And let's let y equal just any multiple of e to the RT. It wouldn't change. I'll just put the a out in front there, but you know where that comes from. Okay? And you can check that, but it's trivial. And that's the same solution you'd get if you use the big P, which would be the antiderivative of 2, which would be 2t in this case, right? You get e to the -2t, just like you get. Okay? So this isn't an important idea here, but it's an important idea in general, because this is exactly how you're going to solve higher order equations with constant coefficients. Okay? And those equations are really, really important, like for damped simple harmonic motion. We've got 10 minutes, we can probably solve that. Okay? We'll just solve one, but I'll then tell you how that gives you your damped simple harmonic motion, maybe. Okay, well, let's say now that my equation is y double prime plus 5y prime minus 6y equals 0. Okay? Well, this is second order. Second order homogeneous with constant coefficients. Now, this only works if your coefficients are constant.
Is it linear?
See any powers of y or y prime or y double prime? No powers. No square roots, no logs, no exponentials of those things, right? So they're linear. Yes. Good question. You know, new terminology, okay? So, second order, homogeneous with constant coefficients. We're going to use the same thing. In this context, most of the equations that we solve, like for simple harmonic motion or a damped, well, like a damped pendulum or for an RLC circuit, these are going to be time-dependent equations. Y is going to be a function of time. Okay? And you know from simple harmonic motion, you get a function of time. So we're going to use T generally when we do this. No reason we couldn't use aardvark for our variable, but we'll use T. Okay? Well, you plug in y equals AE to the RT. What's y prime?
AR e to the
I'm going to
RT.
put the R out front, but yeah, RAE to the RT. What's y double prime?
R squared A E RT
Very
squared.
good. Okay? So, does this kind of remind you of like an eigenvalue problem? It should. Okay. Anyhow, you get r squared plus 5r minus 6 equals 0, which is like a characteristic equation for linear transformation, isn't it? You want to be aware of that because we use a fair amount of linear algebra when we do systems of equations. Just like you use linear algebra to solve systems of algebraic equations. You're going to couch solutions to systems of differential equations, linear differential equations, in terms of the linear algebra. And it's not difficult. The eigenvalue thing is really a pretty easy idea, and we'll come back to you very quickly when you review it, if it's not already locked into your brain. Although it should be, because it keeps coming up in engineering and mathematics, okay? So, you know, from what you learned in linear algebra, what I thought you learned in linear algebra, and what you naturally have mostly forgotten in the last year, it's still there, it'll come back, okay? And it'll be very valuable to you. So we want to reinforce that in this course. Okay, anyhow, you've got this characteristic equation, and it has solutions what? Well, that factors into r equals r minus 6 and r plus 1, right? R plus 6 and r minus 1, sorry. R equals negative 6 or 1. So you have these solutions, okay? And these solutions,
Is B just an arbitrary constant as well?
yeah, well, any solution is a linear combination of these. In particular, the set e to the negative 6t, e to the t, spans the space of solutions, meaning any solution is a linear combination of these. Okay? And by a linear combination,
I'm just gonna step up on this desk, but all right, for all you people who thought I was recording, I did it all.
Yeah.
You can add me in there, I seriously thought I was.
So right there, we found every possible solution. In the process, really should remind you something you should probably review from linear algebra because it's actually fairly simple. Okay? So you really should review the whole eigenvalue problem thing, at least for 2 by 2, 3 by 3 matrices. And what linear independence means. Because you verify this solution by doing a determinant. So in this situation, I could say that y1, y2 is a linearly independent set. If and only if the determinant of the matrix has certain characteristics. Okay? Let's see what the determinant of that matrix would be for this set. Okay? Determinant is this. What's that determinant? It's e to the negative 6t times e to the t. In other words, this minus e to the t times negative 6 e to the negative 6t, which is, that's e to the negative 5t, and that's 6e to the negative 5t, 7e to the negative 5t. It's not 0. Okay? This is a linearly independent set. And the condition is that the determinant is non-zero. Now, zero determinant for matrix is a singular matrix. It's a matrix that represents a system of linear equations that has no solution. Okay? It represents a linear transformation if it's a square matrix. So you can do the determinant whose image space is of lower dimension than the original space. You have all these connotations that you kind of want to get back into your head. Whether, I'm not going to ask you to prove a lot of linear algebra, you're going to use some. Okay? And what you're going to use, in my experience, never gives people any trouble in this course. Okay? It comes right back, and it's pretty easy to use in this course until you get to systems of equations where it's only moderately easy to use. Okay? And then it approaches impossible because things get really complicated. But we don't go to the big complications. Okay? Make sense? Okay. So there you have it. And this is called the Wronskian. Okay? Got it? Okay, again, you're going to have homework. It expands a little bit on these themes, but nothing you can't do if you review a little. Fair enough?